Hello, Oggies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with another episode of Ask Dave. Again, responding to a request from an Oggie. The question was, what's a transponder and how does it work? Well, I've got some charts on that, and it has a lot to do with satellites of all different kinds, including amateur satellites. So let's take a look at what it is, how it works, and who invented the basic technique. We're going to look at transponders in their amateur context. The idea of a transponder is very broad. It refers to something that transmits, and then there's something that responds. And it does not mean that it responds with repeating the same thing that went up or something like that. It could be very different. For example, aircraft have transponders that when queried by FAA radar will respond with required information about the aircraft, like the altitude and so on. Now, in amateur radio, it primarily refers to satellite systems, or what we call orbital satellite carrying amateur radio, or OSCAR. Now, there are not just American satellites up there. There are satellites that come from many people in many countries. These satellites are primarily carried up as ballast on rockets that go to space. Now, the way that works is this. A rocket that goes to space has a certain amount of fuel, it has a certain amount of thrust, and there are a couple different ways that you can steer the rocket. One is to literally steer it so that when it burns out, it's in the right place, or put it on a standard orbit, but then adjust the weight that's on board so that it gets to the right place, okay? Now, you can do some combination of these, and amateur satellites, the original satellites, amateur satellites were quite small. They were primarily carried as ballast on rockets to space. In other words, they got a free ride. And that's still the case today. We're not paying near what it costs to put a satellite into space, which is hideously expensive. Let's talk just a little bit about history. Here is a picture of Telstar. Telstar was a communications satellite that had some of the very earliest transponders. You see these boxes around the side here? These are actually cavity antennas. You can see the little dipole sticking up into them right there. And the RF would come up in one frequency and then go down in another. These up here, which are smaller, would be for higher frequency. I think they were like 6 and 8 gigahertz, something like that. Okay, and the solar panels that were put on these were very early solar panels, and all total generated about 17 watts. Of course, only the part that faced the sun generated power, and the satellite was spin stabilized, hence the need to put these antennas all the way around it. Okay, satellite stabilization is a topic unto itself. Now, I've got to tell you a little story regarding Telstar. When I was a paper boy in probably late elementary school or perhaps junior high school, I was delivering papers one afternoon, and I knew that the initial public Telstar call across the Atlantic would be made while I was on my paper route, and I managed to find one of the places where I delivered papers that let me come inside and watch on television and watch this real time. It was the first time a television image had been beamed across the Atlantic, and it was considered to be a very important moment in history. Well, now the amateur community has been making satellites too. This is phase 3 satellite that we've made. This is a little thruster for burning so you can move it around, get it away from the other components. You see the antennas sticking out over here. All the solar panels, again, spin stabilized. Now, there are two kinds of amateur satellites, the simple kind and the hard kind. The simple kind are the ones that are just FM repeaters. And here is a picture of our club member, Jim Adams. He's got a vertical here that's handheld. I'm sorry, not a vertical. That's a Yagi. Handheld, 3 elements on 2 meters, and let's see, 1, 2, 3, 4, 5, 6, 7 on 70 centimeters. So he transmits up on one band and down on another, so he just uses a little dual band Chinese handheld for this, and it works fine. And with these, all you have to know is the general direction of where they are. They're low Earth orbit, so they're only 100 to 200 miles away, and just a little handheld will reach them. And here's another picture of some other people doing these very simple things. Here's one person with a just a handheld radio with a long antenna, and here's somebody with the same type of thing that Jim had right there, okay? So if we look at the satellites that are on the AMSAT, AMSAT is American Amateur Satellite, that takes care of the American satellites and is sort of an umbrella organization for all amateur satellites worldwide. Has quite a few up. There's quite a few up. Here are the FM repeater satellites with all of the various caveats and so on. It gets a little complicated, but these are FM repeater satellites. Now, these that are called transponder satellites are the ones that use transponders instead of FM. FM and the transponders are very different. The transponder satellites are the classical ones, but they're still being launched today. There are satellites that are FM, are close to Earth, not so close to Earth, and here in fact is one that is geostationary and acts just like a regular communication satellite, like the Intelsats and so on. By the way, Telstar was in a low Earth orbit, like many of the amateur satellites, so its pass overhead was very quick. Now, I want to look at what they call linear or transponding satellites. There's an uplink band and a downlink band. It's not just a single frequency. Okay, the FM satellites operate on a single frequency. A frequency for the uplink usually on 2 meters, and on downlink, which could be on 70 centimeters. They switch them around, different types of things here. But these satellites have not just a single frequency, but a band of frequencies. So you can have multiple users. This is an old one, AO7, which is only active in sunlight because the batteries are long, no good. Okay, and it goes up on 2 meters and down on 10 meters. Okay, all of the newer ones, like this one right here, AO7 Mode B, is up on 70 and down on 2. AO73, which is a fairly new one, is up on 70 centimeters and downlink on 2 meters, and so on. They're all a little bit different. Now, I want to show how this works. How do you get an uplink from here down to here and do it for a whole band? Well, to do that, I have to introduce our scientist. He lived around the turn of the 20th century. His name was Reginald A. Fessenden, and he was a Canadian scientist who discovered and developed what we call today heterodyning. By quote, mixing two frequencies together two new frequencies appear. These are the sum and difference frequencies. This basic principle, and I do mean basic principle, is at the heart of all super heterodyne receivers in use today. It's finally, we're edging a little away from it with digital, but still, it's still very, very important in radio, okay? And he discovered that if you take two frequencies and you mix them, quote unquote, together, you get two new frequencies, the sum and difference. Now, mixing does not mean what audio mixing means. Audio mixing is where you get a bunch of instruments and you mix them together. You're really summing them, adding them, okay? And you can do other things to them, like compress them and so on. But mixing actually in this context means multiplying. And you can do that with any non-linear device will cause mixing, okay? And I'm not going to dig into mixers to show how they're done. I've got other videos on that. But if you'd like, in the Amateur Radio Handbook, there is a complete set of all the mathematics required to show how the sum and difference frequencies are created. Now let's take a band of frequencies. This is the big conceptual leap here, okay? Rather than take a single channel or a single FM channel or a single sideband channel or a single CW channel, we're going to take a group of signals. This happens to show the entire 20-meter band earlier today. These are your digital type stuff over in here. Here are your sideband over here. Here's your CW down here, okay? This is the entire thing. Now, this is a little easier to understand now because a software-defined radio can take an entire set of frequencies and do things with it. In fact, in this software, which is SDR Play, SDR Uno. SDR Play is the name of the company. I used an RSP1A, which is a radio spectrum processor, Model 1A. And it puts up the whole spectrum here. And then you can take little software receivers and put them on individual signals. But what a transponder will do is take a band of frequencies like this, a whole spectrum, and change the frequency of the package of frequencies to something new. Now we can take either the sum or the difference frequency. Let's take a look at what happens if we take the sum and difference here. Well, our frequency A will be a megahertz out of the 4 megahertz 2-meter band, 145 to 146 megahertz, okay? Now I've got a local oscillator here at 290 megahertz. What's going to come out? Well, frequency A will be this over here. Frequency B will be the 290 megahertz. We will have the sum, which is 435 to 436 megahertz. Remember, we've got a band over here. And the difference happens to be 145 to 144 megahertz. It's been flipped over, and it's at a very inconvenient location because it's too close to this stuff here, and it's hard to keep all that stuff apart there. Now, I want you to note the frequency inversion right here. What went in is 145 to 146, comes out as 1545 to 144. Let's use a different frequency for the local oscillator. Let's use 581 megahertz. Okay, now we get 145 to 146. We get our 581. The sum 145 plus 581 is 726. 146 plus 581 is 727. We have no interest in these, so we will filter them out. The one we are interested in is the difference frequency. Now note that the difference between 145 and 581 is 436 megahertz. Okay? Here's conceptual leap number 2. 581, the difference from between 581 and 146 is 435 megahertz. Look what's happened here. We flipped it upside down. Okay, so we have what's called frequency inversion. Upper sideband becomes lower sideband and vice versa. Let's look at how this works. This is that spectrum that I showed you earlier. Now I'm going to invert the spectrum over here. Okay, now if I invert the spectrum, the FT8, instead of being down here, is up here. And note that the signal that is above FT8 down here is now below it. So if you take an upper sideband signal from here, it becomes a lower sideband signal over here. If I put a CW signal in, it becomes a CW signal out. If there's a CW signal that's above it, it's below it here. Okay, that's very important. Now, since we are transmitting a broad band of frequencies instead of a single one, we have to put in enough power to cover this entire spectrum. Because if this is a 5-watt handheld signal type of thing, well, here's another 5-watt handheld signal. Here's another one, here's another one, here's another one. And you literally have to add up all that power. So you end up with more complicated antenna arrays. Here, this is a helical loop. See the helix right there wound around this little tower element. Okay, here's another helical loop. It's a circularly polarized. And note the way this is on here. This is got a rotator on it that rotates both in azimuth and elevation so that you can point at the satellite. Usually, instead of doing this sort of by guess and by golly type of rotation, because these antennas are such higher gain, you've got to be much more accurate in pointing. Now, some of the advantages of transponders. Several people, several hams, can use the satellite at the same time, okay? If CW theoretically doesn't. Now, I showed the whole 20 meter band, but if you look at the actual frequencies, the links aren't that wide. 142, 125 to 175, that's a 50 kilohertz link, okay? And a 50 kilohertz downlink. This one here we have 20 kilohertz, okay? So the concept is the same as these things I was showing you here, but it's a much smaller slice. So obviously people are encouraged to use CW because you can get more signals in. If you use sideband, you're going to have to put a lot more power up and it's going to take more of the bandwidth, but it can be done. Now, the transponder itself is easy to make. It's no more exotic than a stable local oscillator, a mixer, and some filters. And that's it. It's pretty simple what's in the satellite. But there are disadvantages to transponders. The biggest of them is this, that power management is required, okay? Power management is required on the part of the people transmitting up. You are transmitting into a shared resource. And the satellite's limited power, which it gets from its solar cells, is spread among the entire downlink. Okay, so if some unscrupulous user puts up a really strong signal, it'll stand out in the bandwidth, like these FT8 signals stand out here. And here's a couple standing out over here. They're going to hog the downlink power. Okay, so you've got to be very careful. Usually people who are using transponders will have a radio like an FT991A, and they will be listening to the downlink at the same time that they're transmitting. so that they can make sure that their signal is about the same level as everybody else. Another thing that you have to do is account for the Doppler shift. The Doppler shift it's just like the Doppler shift you hear when a train horn goes by. As the satellite approaches you, the frequency is higher. As the satellite goes away from you, the frequency drops. And it can drop enough that it'll move your signal right on out of the passband that you're listening to. So you've got to be ready for it. A lot of hams just track this manually by listening to their own signal, listening to the signal from the other person. Remember, the Doppler shift can be affecting your signal differently from the way it's affecting somebody else's signal, because you might be sitting here with the satellite going away from you, while the other person is sitting there with the satellite coming toward them. The other thing is that larger antennas may be involved. These antennas must actively track the satellite as it moves across the sky. The only exception to that is the geostationary satellite, but that satellite is so far away, you need a pretty serious antenna to get to it. Okay, and you need 2-axis rotators, azimuth and elevation, in order to do that. So, okay, I've kind of answered the question, what is a transponder? A transponder is just this. It's the radio part of the satellite. It takes in an uplink and changes the uplink's frequency to a new frequency, and in the process of doing it, usually ends up inverting it. Okay? So this would not work terribly well for FM, plus FM will hog the entire band for one channel. USB you can get, let's see, in 20 kilohertz, you can get 6 or 7 signals in there if they're not over on top of each other, okay? So some satellites are easy. These are the ones, when people say satellites are easy, these are the ones they're talking about. It's the FM repeater satellites. Some satellites, in other words, the transponder satellites, can be a bit more complicated, which makes them more challenging and hence more rewarding, and requires radios that do CW and sideband on 2 meters, 70 centimeters, and sometimes other frequencies, microwave frequencies, okay? Some of the transponder satellites are at quite a distance from the Earth, which means now the lower satellites orbit very quickly. As you get further out, the length of the orbit increases, which means the pass time can be quite long, even hours. And if it's in geostationary, it just stays there and doesn't move. But there's just one of those, and it's not really where we can use it. It's over the Middle East. So the pass time can be quite long with the satellites that have like Molniya orbits or other weird elliptical orbits. And you can have fairly lengthy QSOs with people who are very, very far away on the planet. So there you go. We have talked about transponders and how they move frequencies or band of frequencies to another band of frequencies. We've talked how they can invert. We've talked about how you need bigger antennas for those rather than the simple little antennas like Jim in the snow out here. And we've talked about that there are quite a few satellites that are on. And we gave credit to the guy who discovered heterodyning, and that's Reginald Fessenden. By the way, Reginald is not the inventor of the superheterodyne. That was Major Armstrong. Well, there you have it, transponders. In amateur radio, they're largely used in satellite. A transponder is anything that is queried by a ground station and responds in some manner. That can be things other than communications, but in amateur radio, we're primarily using transponders for communications. So I hope that answers your questions today. If you would like to support this channel financially, you may do so. You can come to dcasler.com support and look at the various different ways of supporting the channel. Also, please subscribe and click like, and until we next meet, 73.